already once, 100 years ago, what we think the purpose of physics is. Gone was the idea of Laplace's dream of classical determinism, and instead we're just left with the inevitability of making statistical or probabilistic predictions about nature, with things like the uncertainty principle being one of the hallmarks of this very, very peculiar fact about nature. We can't both know the position and momentum of a particle at the same time, which is a prerequisite for being able to predict where it goes next if you have a classical picture of the world. Now, as I said, the synthesis of these two basic ideas, just of relativity and quantum mechanics, putting them together turned out to be a remarkably challenging and interesting thing to do, and really, quite surprisingly, we're still coming to grips with the full nature of what this synthesis can do and what sorts of phenomena it can generate and what it can explain. But it was not easy to put together special relativity and quantum mechanics. The synthesis of the two of them that was completed in the early 1930s is called quantum field theory. And it has many remarkable consequences, but there's one of them that I want to highlight because it'll be important for some of the rest of the story. One of the amazing consequences is the existence of antiparticles. So if the world is both relativistic and quantum mechanical, necessarily antiparticles must exist. And this is a sketch of an argument for why this is, which is commonly given. There are holes in this argument, but it suffices for this purpose. If you imagine, this is a sort of classic space-time picture that you're familiar with when you study, if you study special relativity. So imagine an axis in one dimension of space and dimension of time. Light would move on 45-degree lines in this picture. A particle that's just sitting at rest would just sit here and move on and on and on. A particle that's moving a little quickly would just, would move along a line like that. A particle moving at the speed of light would move right along at this 45-degree line. But imagine that something could go faster than light. So imagine you had something here and you shoot it and it goes faster than light, so at a more than 45-degree angle here, and it makes it from the point A to the point B. You open up textbooks and they tell you that this can't happen because if it did happen if it did happen, it would be possible to violate causality. And the argument is that in another frame of reference, in a sufficiently boosted frame of reference, you could make that event B happen before the event A. So it looks like you're sending a signal backwards in time from the point A to the point B. That's a classic reason in classical relativity why it's impossible to transmit signals faster than light. It's simply inconsistent with causality. On the other hand, in a quantum mechanical world, we can't be precisely sure where this event took place. There's always some small chance, in some sense, that it actually took place a little bit over to the side, and it really did make it from A to B in a way that appears causal, but you actually can't tell. You can't tell if it went from there, you can't tell from where exactly it went from. So there is some frame in which it might look like the inference went, where the signal went back in time. The only possible way to rescue a causal interpretation for what's going on is to say, no, there's no negative charge going back in time from A to B. Instead, there's a positive charge flowing forward in time from B to A. So this is forced on you. It's forced on you if you try to make quantum mechanics, causality, and relativity all consistent with each other. But that means that there must be something out there, there must be a particle out there in nature with all exactly the same properties as the electron, but with opposite charge. So you could have this interpretation. So that's why, that's at least a cartoon of an argument why relativity and quantum mechanics together force the existence of antiparticles. Another example of a case where the prediction was too dramatic for the author of the theory to make, in this case Dirac, really refused for a long time, at least 3 years, to actually say that his theory predicted that this antiparticle existed, despite the fact that it does, and it's correct and it's out there. So this is really fascinating because this extension of our notion of space and time that was given by Einstein, combined with quantum mechanics, doubled the world. Okay? It meant that there had to be a whole other set of particles out there that had never been seen before until they were. But it's just an inevitable consequence of this extension of the notion of space-time given by Einstein combined with quantum mechanics. I go through this example here because when we come later to talk about supersymmetry, we'll see that there's an almost literal, exactly same set of words that we'll say associated with that picture of the world. All right, well, one of the important consequences of the existence of antiparticles is that space-time keeps acquiring more and more structure. Okay? So beforehand, Newton, it was this static arena in which things took place in space separately from time. In special relativity, space-time get mixed up with each other. It's still a static arena. In general relativity, it can have some dynamics. It can stretch. That's associated with gravity. But still, there is a notion of emptiness. There's a notion of there being nothing. And this combination of quantum mechanics and relativity even removes that. So even the vacuum has some very interesting structure. The reason is, if you try to check whether some region of space-time is empty, so as I'm sure you've seen, all my drawings are terrible. So you'll have to put up with this being a magnifying glass a number of times, okay? So I apologize. But anyway, if you take that magnifying glass and you look at a little region of space to try to verify that it's empty, the problem is that because of the uncertainty principle, you have to put some minimum amount of energy into that region of space. And as the size of that region gets smaller and smaller, you've got to put more and more energy into the little region of space you're trying to verify is empty, until you put so much energy into that little region of space that nothing can prevent you from producing an electron, and it's anti-electron. You conserve energy, you conserve charge, you conserve everything. Without antiparticles, that wouldn't be possible. But with antiparticles, it's perfectly possible. You conserve energy, you conserve charge, you conserve everything. So the act of trying to verify that the vacuum was empty yields an electron-positron pair. Okay? Any experiment that you might want to do that would check that some region is empty will produce particles. Okay? The world is quantum mechanical, so it won't do it the same way twice. Okay? So you'll get a whole distribution of different things coming out. But whatever's out there, you will eventually see it if you use a fine enough magnifying glass. So if you had this picture of an electron with all these lines of electric force coming out of it, that picture is really not quite right. There isn't emptiness surrounding it. As you go to shorter and shorter distances, you find that if you did any experiment to probe what's going on there, you would find evidence for particles and antiparticles, which we picturesquely say are popping in and out of the vacuum at all times. But that picturesque notion is really a stand-in for the fact that if we do any experiment, we'll see every now and then, oh, an electron-positron will come out. Or if I look at even shorter distances using higher energies because of the uncertainty principle, a muon and anti-muon would come out. Or other particles. Anything that's out there with a sufficiently strong magnifying glass, we would see. Often people describe large accelerators like the Large Hadron Collider as the world's most powerful microscopes. And you might imagine what the microscope is looking at. It isn't looking at a cell or a piece of hair or something like that. It's looking at the vacuum. So it's the most powerful microscope looking at the vacuum. And again, because the world is quantum mechanical, it's actually taking a snapshot of this roiling mass of stuff going on at all times. It doesn't look the same way twice, but we learned something about the properties of the vacuum by building these gigantic accelerators. All of these developments, putting together quantum mechanics and relativity, this basic rubric of quantum field theory, culminated into the 1970s into a very specific quantum field theory that people found actually described all the particles interactions that we've seen. Its overly modest name, if it was in this epoch, it would have been called the most super duper theory of everything. But back then, it was called the Standard Model. And it's really a stunning accomplishment. It is just realizing that putting together quantum mechanics and relativity goes shockingly far. We didn't really need, in the end, to change in any fundamental way the rules that were handed down to us by Dirac, Born, Heisenberg, and all their friends, taking those rules very, very seriously and figuring out all of their consequences and pushing it as much as possible. This very specific quantum field theory was described that really describes everything in a really remarkable way. So every interaction between all particles and all interactions are associated with little stick figures like this. The electromagnetism is associated with a stick figure representing the interaction of electrons with a photon. The weak interactions responsible for radioactivity are associated with exactly the same kind of stick figure, giving us interactions between electrons, W particles, and neutrinos. The strong interactions, quarks and gluons, There are some detailed differences. The gluons interact with each other, the photons don't, and so on. But in the end of the day, there's one basic common mathematical structure that really allows us to describe everything. The remarkable thing is that this structure only became manifest, and this great similarity between these different interactions only became manifest at short distances, at distances around 10 to the minus 16 centimeters. In a sense, that's because of some from the short distance or high energy point of view, not particularly fundamental differences between them. That the W particle, for example, has a mass. It can only travel around 10 to the minus, with a characteristic distance around 10 to the minus 16 centimeters. The photon is massless and can propagate over very long distances. From the point of view of a very short distance, the very short distance physics, that's not a very, very big difference. From our point of view, where we live at very long distances, it's an enormous difference. But it's only illusory. This difference between them is simply because we were stuck for 2,000 years, only being able to probe distances much longer than 10 to the minus 16 centimeters. And this fundamental similarity between all the interactions only became apparent when we went to short enough distances. That's the reason we do particle physics. At least there's a way of talking about the subject, which is about figuring out the ultimate building blocks of matter and words like that. At least I don't find that kind of argument very, very compelling. The sort of Russian dolls all the way down picture of the world isn't necessarily all that interesting. The real reason we do it is because we've learned through experience over and over again that this essential unity and simplicity of the laws, the fact that they all look the same, that we can even contemplate them all looking the same really for the first time, becomes apparent at short distances. That's why we go to short distances. We want to learn something about the laws, not necessarily the sort of a suite and spectrum of particles that are there. There's one thing which is left in this picture. So I told you that this theory, in principle, anything at sufficiently long distances, 10 to the minus 16 centimeters and longer, is incorporated in it. For example, you can ask, why does a particle like the electron have a mass? It's very important the electron has a mass. If it didn't have a mass, atoms wouldn't exist or would be infinitely big. So this is, again, a very basic feature about the world. Why do atoms have a finite size, small size? Why do electrons have a mass? This, unfortunately,